So we have been working on the Zero Knowledge State channel for quite a while now, and for ZK Summit 9's ZK Hack competition, we thought we would take another stab at building it from scratch, this time using the Plonky2 Zero Knowledge Proving System. And this time we were actually successful, a little bit surprisingly. What we have here is absolute basic proof of concept of what it could do, what it could be. There's a lot of stuff that is ultimately missing, but just to do the absolute bare minimum, we've shown basically the full steps of a zero knowledge state channel. So a zero knowledge state channel is essentially a novel mechanism for enabling both privacy and scalability on EVM blockchains. And this is actually something that will stack very cohesively with layer 2 to enable further scalability. So essentially the value proposition, at least on the scalability side, is that we, instead of having to post every state change on chain, whether it's a layer 2 or a layer 1, we instead construct a zero knowledge circuit that allows us to pass proofs back and forth over peer-to-peer connections to build ultimately the final state without a validator or a sequencer. So obviously this has awesome implications for scalability when we can batch a bunch of transactions into a single transaction, essentially, a bunch of state increments into a single transaction. There's also the ability to use this same mechanism to actually obscure the execution of the state channel and provide privacy as well. So essentially what a state channel proof does is summarize a bunch of sequential state executions, and we can choose which parts of that state execution we want to actually reveal publicly, which parts we want to be completely shielded in zero knowledge terms. So we've been working on Battleships specifically because Battleships is a fantastic example of adversarial, multi-party, hidden information game. And while this is a bit of a mouthful, this actually is a very common economic relationship. And by demonstrating the zero knowledge state channel in something trivial like a battleship game, we think that it'll be a lot easier to extend this to something more meaningful, beginning with invoice factoring and hopefully going on to things a lot less inside the box. So there's definitely a lot missing. Again, this is an absolute proof of concept that we whipped together in a couple of days. But this is our very simple demonstration of what a zero knowledge state channel essentially looks like with respect to a battleship game. So there's, and we'll get into this in the code in a moment, but there's essentially 3 phases in a zero knowledge state channel. There is the channel open, which is done once. There's the channel increment, state increment, which is done as many times as needed. And then there's finally a channel close proof, which is also done only once. And then these outer proofs are essentially the vehicle by which we drive the game logic. So for the channel open, how that works is that we get a commitment to a board from and prove that that commitment is valid from Bob and Alice, host and guest, and then we can pass that back to the host, who actually runs the channel open proof, demonstrating that there are 2 valid boards and a game can start. And then for every single state increment, we essentially are taking the previous state increment proof, which at the very beginning can be the channel open proof, and combining that with a shot proof, which is basically evaluating whether or not a given shot hits or misses on a board commitment in zero knowledge. And we basically recursively pass these back and forth the same way as would be done in an on-chain zero-knowledge battleship game, as we've actually demonstrated in the past. However, all of this, again, is being built up with PCD recursion in such a manner that eventually we reach the channel state or the channel close proof. And we can use this proof basically to verify that in our case of Battleship, there's 5, 4, 3, 3, 2 positions for the 5 different ships. Those are the lengths. So that sums up to 17. And when we identify that this recursive state building has found 17 hits on either player, we can then actually create a channel close proof, which is a single state object that represents the entire game. And again, this is done without any sort of sequencer or third party responsible for anything. And again, while this is not yet completed, we eventually will take this channel proof and using something like Plonky2 Circom, we will post this on chain. And this can become super interesting because we have obviously proven the scalability aspect by batching a bunch of transactions into a single on-chain transaction. However, we can also use it for privacy-preserving mechanics. So the case that we're using in Battleships, once we get it working, is to essentially generate an ELO score based on you winning or losing. So this channel close proof is basically going to be a proof that a Battleship game occurred where Alice won and Bob lost, and there's going to be absolutely no other state that's revealed. And that can be thought of as like private qualitative state that is derivative of your performance. And in public, we want to have some sort of quantitative score that is provable in that it is actually based on your performance. But doesn't reveal all that, all the stuff that happened to actually earn you that score. And this is essentially a way for us to demonstrate how zero-knowledge state channels are a mechanism for some sort of performance or credit scoring, as just one of many examples of how this might be used as a privacy-preserving technology. So we'll do a brief walkthrough of the code. Essentially, and really all we care about are the circuits. There's two groups of circuits. There are the game circuits, and these are essentially the exact same as some of the other Battleship, like if you look at Circom or Noir, these circuits here are essentially the exact same. Perhaps a little different in execution, but in spirit, exactly the same. Whereas we also include our channel proofs. And this is where it gets interesting. So we have open channel, increment channel, and closed channel. And I'm just going to go into closed channel as that's where the actual test that we'll show you in a second is run. But we can see open channel. So this is essentially where we take board circuits and prove that there are two valid board commitments that can be used to start a game. And then we have the increment channel state proving function, which essentially just takes a shot circuit, which is proof that a given shot hits or misses a given board commitment. And again, as mentioned previously, this incremental channel state relies on information from the previous incremental channel state proof and recursively builds up specifically the damage values here. So we want to see one of these values hits 17. And once we do have one of these values as 17, we've reached an end condition which allows us to create the final zero-knowledge proof that is a state channel. And just while we're on these end conditions, this is a big difference from legacy or optimistic state channels, which is that you just can't post a zero-knowledge state channel, at least in our construction. You can't post a zero-knowledge state channel on chain before it's released or before it's achieved one of these end conditions. But also, once it has reached one of these end conditions, there's no such thing as an optimistic challenge period. You've verified in zero knowledge that the state that you're attesting to is correct, or the state that you're posting is correct, and therefore the finality of a state channel proof, a zero knowledge state channel proof, is instant. So in short, we basically go open channel, recursively increment the channel state as many times as we need, and then finally, once we've reached the end condition, we can prove the closure of the channel. And in the future, we would then take this and post it on chain, and as mentioned, do some fun things like ELO scores, or something more exciting if this were to be applied to something more realistic. So for the sake of time, we're just going to show the very end of the execution of the full state channel test that we've written. But there are a couple of other videos that we've posted on the BattleZips channel that show a little bit more of this, as well as you're welcome to actually download the code and run it for yourself. It is, of course, very slow. You'll see in a second it took literally 2,000 seconds, but that is also hundreds of, well, dozens at least, of proofs. I think it's about a proof a minute with multiple proofs inside of the outer proof. So while this is maybe not great for battleships, it definitely would work for something like invoice factoring, but as you can see, it works.